Hello Minecrafters, and welcome back to another Redstone video. Today I have something really crazy to show to all of you. Today I want to present to all of you a super powerful Turing machine in Minecraft using only Redstone. Now I will gonna talk a little bit about the spec of this thing, so you will gonna know how powerful this thing actually is. First is the tape itself. The tape can store 16 symbols, including the blank symbol, and it can also be expanded infinitely as long as you want to hold even longer data string to operate on. Next is the instruction table, which is this very ginormous thing right here. This instruction table has in total 16 states and 16 symbols, meaning you can actually have a program stored in this instruction table that is 256 instruction long. So a very powerful instruction table to tell the Turing machine what to do. Before we get into the meat and potato of today's video, I just want to thank the Super 997 for coming up with this idea. I did not come up with this idea, it was his idea, and his idea was to create a very powerful Turing machine that has 16 symbols and 16 states to fully utilize the hex or signal strength system of Redstone Dust. Now my implementation of his idea is a bit different from his, and currently he is working on his own version with his own implementation, so I will gonna give an eye out for that, and when he release a video about his Turing machine, I will gonna link his video in the description of this video. But yeah, thank you so much to the Super 997 for giving the idea in Wings Discord server. I was fortunate enough to be there, and I really glad that I came up with this approach right here. Alright, without further ado, let's get right into today's video. The first thing that we were gonna do is talk a little bit about Turing machines, because well, I think some of you don't even know what it is. And don't worry, I will not gonna go into the theories of Turing machines because they are very complicated and I don't fully understand them myself. So I was just gonna give you a very brief explanation of how a Turing machine works. Alright, so in order to explain this a bit easier, I have drawn here the blueprint of a Turing machine. So the first thing that a Turing machine has is a tape. This tape is infinitely long, and the tape is divided into squares. Each of these squares can store a symbol, and it can be any kind of symbols that you want. Another property of the tape is it can move to the left by one square or to the right by one square. So yeah, that's basically the tape. Next is the head. The head can basically read the symbol or write a new symbol to the square that it is pointing at. So right now this head right here is pointing at this symbol, so it will gonna read the $sign symbol here, and it can also write a new symbol, so overwrite this symbol with a new one using the head right here. Finally, the most important thing about a Turing machine is the instruction table, and this instruction table is basically where our Turing machine program will be. So an instruction table has a bunch of rows and a bunch of columns. The columns are for the symbols. As you can see, we have A here, $sign, stars, and 4 here, and then this symbol, which is basically blank symbol. At the rows we have what is called states. So state is basically a way to show the present condition of the Turing machine. So it's a way to track where the Turing machine is in this instruction table. Okay, these states and these symbols, when combined together, creates this grid of squares right here, and in each of these squares or cells that we like to call it, there are 3 parameters right here. The first parameter basically stores the new symbol that we want the head to write to this square right here. The second parameter, we're gonna tell the instruction table the new state that it needs to shift to, And finally, this parameter right here basically tells the tape if it needs to move to the left, to the right, or stay still. And one more thing about the instruction table is it has something called a holding state, and it is essentially a signal, and when the Turing machine reaches one of the squares that contains this like signal right here, it just stops. So the machine just stops. And yeah, that's basically how a Turing machine works. In order to understand Turing machines a bit better, let's do an example. So here I have like an exercise that we can do together. The goal is to copy the symbol on the right of the binary strings to the left. So here is the binary string that we have, and the goal is to copy this number right here, so number 1 here, to the left. And here is the instruction table that we have, and now if we just follow this instruction table, we should be able to turn this to that. Alright, let's do this. Now, one thing I forgot to tell you is that when you start like executing the instruction table, we always start at S0. Okay, next is the head. The head will gonna be at the beginning of the data string. It can technically be anywhere in the data string, but the most common place for the head is at the beginning of the data string, which is here. Okay, alright, now let's get into like actually doing the program. So the head is over here, and now we look at the instruction table. We know that we start at S0, and the head is currently reading 0, so that means we're gonna execute this instruction right here. Now this instruction basically tells us to first write a 0, that's the first parameter, so we write a 0 here, which it is 0 now, so I don't have to do that. Okay, next it tells us that we need to go to S0, so that's the second parameter, and now we go to S0. Then it tells us to move the tape to the left, so -1 is actually left, and 1 is actually right, and 0 in the instruction table is basically stand still. I will mark that as S. Okay, alright, so we move the tape to the left, so now the head will go from here to here, and then we basically just repeat the process. We know that we are still at S0 from this instruction, but now the symbol is 1, so we execute this instruction, and it tells us to write a 1, go to S0, and move the tape to the left. We keep doing this until the tape reaches this point right here. Now if we look at the instruction table, it tells us that we know that we are at S0, but it is a blank symbol, like the head is reading blank. So we basically execute this instruction. This instruction tells us to write a blank symbol here, go to S1, and then move the tape to the right. So now the head should be here, but now remember we just went to S1, so we need to look at S1 now. S1 here, and symbol that the head is reading is 1, so we'll execute this instruction right here. So this instruction tells us to write a 1, go to S3, and then move the tape to the right. So let's do that. We move the tape to the right here. Okay, and if we look at S3 now, we know that we have S3 here, and then the symbol is 0, so we execute this instruction right here. So we write a 0, go to S3, move the tape to the right, and we keep doing this until we reach this point right here. So now the head is here, and if we look at the instruction table, we know that we are still at S3, but the symbol is now blank. So we execute this instruction right here. This instruction tells us to first write a 1 here, and then move to S4, and then don't move the tape, so the tape stays like this. And if we look at S4 now, we see that these two like cells right here are actually blank. So we know that we are looking at 1, we are at state like state 4, but there's nothing here. Now this nothing cell indicates that there is a halting signal here. Okay, and now that we know that we have reached a cell that has this halting signal, we just stop the machine. So yeah, the program is finished. And for these like cross here, that basically indicates that this area is not accessible by the program. But in the actual programming of my Turing machine, you don't actually need to do this. You can just ignore them. Okay, now if we check the result, we can see that yeah, we have a 1 here. So now if we check, we have 1, and then we have 0, 1, 0, 0, 1, 0, 0, 1, and then a bunch of blanks here. And there we go. Just by following this instruction table right here, we basically turn this data string into this data string. And that's basically how a Turing machine works. The only thing that is difficult about this is basically coming up with this instruction table right here. Every single like task is like writing a programming like a program similar to how you would do coding. And yeah, this basically just like Turing programming language, if that is a thing. I call them like that because it sounds like it sounds fitting to me. But yeah, that's basically it. And yeah, now we can get into the actual like Redstone part, so we can like dive into how everything actually works Redstone wise. Alright, back at Minecraft. Now we can start digesting all of this Redstone spaghetti right here. Don't worry, it looks complicated, but it's actually not that bad. Okay, I promise. Okay, I will try to make this as simple as I can. Alright, first is the tape. The tape has copper bulbs as a way to store the symbols, and the reason why I have like 4 piston V tapes here is because, well, we have 4 bits, and 4 bits can basically represent 16 different symbols from 0, 0, 0, 0 all the way to 1, 1, 1, 1, as you can see. Also, we have a way to extend this piston V tape as long as you want. You just need to keep in mind that when you look forward, so in front of the slump block or the honey block like this, make sure that there are only 9 blocks, okay? Only 9 copper bulbs in front of the slump block or the honey block, because if you go further, the thing will gonna get jammed because of the push limit. Down here I have a like another piston V tape which basically controls the reset line, because we basically want a way to clear the tape, right? So we have a bunch of signals here, right? We write a bunch of stuff, and when we want to clear, we don't have to we don't want to go into individual copper bulbs like this and change, right? We don't want to do that, and I accidentally break that, so let me fix it. This is bit 2. Alright, that is not in the script, but yeah, basically you don't want to go into individual copper bulbs and replace them like that, right? You want to have a way to automatically do that for you, and you can do that with this node block right here, which basically just cycle the copper bulbs around, and when a lit copper bulb in contact with this circuit right here, so when a copper bulb here is lit up, this comparator will turn on, powering this piston right here, which pushes this observer into this block, powering the copper bulb to turn it from on to off. And yeah, that's basically it. Nothing too much, nothing fancy, and yeah, the redstone I try to keep it as simple as possible. And yeah, that's basically the tape. Oh wait, I forgot about one thing, which is the moving left and right. Well, the moving left and right is right here. These 2 sets of piston right here, and they are controlled by these piston right here. If you, let me get a redstone block, if you like power this piston, I'm gonna tick freeze so we can see this a bit easier. So when we tick freeze, when we activate that pistons, we will see that, yeah, you can see that these pistons push the copper bolts to this side, which is basically to the right. And if we do that to the other pistons, so again I'm gonna tick freeze so we can see it a bit easier, and then I tick unfreeze. You are gonna see that these sets of pistons, this piston activates, pushing the copper bolts to this side. And as you can see, the feed tape is a two-way feed tape, the tape can actually move left and right by one block like that. So yeah, that's basically the tape. Now I will gonna get into the head. The head is basically this light gray circuit right here. We have a way to read, which is through these comparators right here behind this toggle block. So let me activate one copper bulb right here. So when we do this, as you can see, this comparator lights up and powering this part right here, which goes into this part, but we were gonna talk that part later. But yeah, we can read the copper bulb like that, and we can also write to the copper bulb, and we write to that copper bulb using this part right here. This is basically where we're gonna send the signal in. So let's say I want to send I don't know, like this number, which is 10 in binaries. And now if I activate this line briefly, so like this, as you can see, now we have a 10 here. And if we change, like if I change this to, let's say 7 in binary, and then I do this, we should get a 7, as you can see. So yeah, that's basically how we're gonna write to the to the tape. We first provide with the symbol that we want, and then we activate. We basically post this line right here, which basically just unlock all of these comparators, as you can see, because well, they are subtracting 15 minus 15 is 0, but when we remove this, now it is 15. But when we put the repeater back, now it is 0, because they are subtracting. And yeah, that's basically how you were gonna write to the tape and read from the tape. And yeah, that's basically the tape and the head. Now all of the other mess are actually for the instruction table, and I will gonna start at the actual instruction table itself, and then I'm gonna explain all of this mess right here. And don't worry, the instruction table is not that bad. Okay, so the instruction table starts here. This is S0 and symbol blank. Now in each of these cells there are 4 distinct parameters. So the first parameter is this orange line here. This is the halting signal. So when this signal is on, it will basically go to the Turing machine and stop everything here. Just stop the dynamic clock that I have in the Turing machine. Next is this line right here. This red line is the second parameter, and it tells the tape which direction to move. If you look over here, we can see that the red line basically controls these 2 pistons, and depending on which redstone lines here turns on using this red coder here, the corresponding piston we're gonna extend, powering the corresponding sets of piston here to move the tape either to the left or to the right. And yeah, that's basically the red line. Next is the brown line. The brown line is the third parameter, and this brown line we're gonna tell the Turing machine which states to move to, and I will talk about that later. Finally is the black line. The black line is the final parameter, and it indicates what symbol we want to write to the tape. So it tells the head what to write, and if we just follow this black line, we were gonna see that it goes into this very bulky red coder here, which encodes, which basically re-encodes hex signals or signal strength into binary string. And if we follow this light gray line here, we go back to here. And if you remember, this is where we're gonna provide our like symbols to the head, so the head can write to the tape. And yeah, that's basically what the black line does. As for the brown line, we were gonna get back to here. The brown line will basically go to this brown like red coder here, and again it will go, this red coder we're gonna turn signal strength or hex values into binary string, and the binary string will go back to the instruction table. Because remember, if you remember from the example, we basically just look at the state, like the new state after one instruction is executed, right? So we basically just feed the output from this from this red coder here back to the instruction table. And now is the dumb part here, this yellow part right here. What the hell is this? Well, this is actually how we can select individual cells in the instruction table, because remember, we need to select like each cell every like cycle in the instruction table, right? And this is how we select like the instruction, like the cell in the instruction table. And it looks complicated, but don't worry, it is not. This thing is actually just like a very big, very big matrix decoder. Now that sounds complicated, but it's not, okay? It's just two very simple and standard decoder that you can actually find in MathBatWing's like logical redstone reloaded series. I will link that in the description. So it's basically just two very standard decoders, and yeah, very standard one, and they basically cross each other. And when both decoders turn like off, like select one, so for example, it select this, so this decoder select this right here, so all of the lines here turn on, and then this decoder select this, so now all of these lines, like this line, we're going to turn on, and the cross section between those two outputs will be connected here. So now only this cell is off, which no, not off, but like being chosen. So now only this cell is like being chosen, and the information or the instruction in that cell will get sent to the output of the instruction table. And yeah, that's basically what this very bulky YOLO circuit does. It basically allows us to individually select the cells that we want in the instruction table. So yeah, that's why when we want to read a new state, we just feed the output of the instruction table, like the state output, back to the instruction table for further processing. And over here, we need to read the new symbol on the tape, right? Because the tape, not the tape, but the instruction table has symbols and rows as their coordinates in the instruction table, and we need both of them in order to actually find the cell that we want. So we take the signal from the head. So yeah, we take the signal from the head here, and then we just put like input the symbol to this decoder right here to find the exact column that we want that the cells on. And then here we basically feed the state in to find the exact row of that cell, and we find the cross section between the symbol and the state to find the exact like cell that we want. And then the output of that cell will go to like the output here. Like this is the output of the instruction table, and then we just loop this until we find a cell that has the halting signal. Then the orange circuit here, which is the halting signal, will just basically cancel everything, like cancel the clock, cut the clock off, and yeah, everything should stop. Now of course, because there are 16 symbols and 16 states and I want this to be compact, I decided to use signal strength, like encode everything in signal strings. So I have signal strength memories in here to store the exact signal strength and stuff like that. So it's kind of slow because of all of these comparators, but I think it should be fine because we have a tick rate command, right? Because we are in 1.21 plus, so I don't think it should be a problem. Finally is the like the blue line here. This blue line is basically a line which clears the program. So we have a way to clear the tape, basically the data string, and we have a way to clear the program, so you can actually program multiple programs on this Turing machine right here. So it is considered a universal Turing machine, which is really nice in my opinion. As for this green circuit here, this green circuit is basically a way for us to select a specific cell in a particular row for us to write instruction to it, and that is something that I will gonna get into right now, which is like how to actually use the thing. Now I will gonna teach you how to actually use this thing, because it's actually not that hard. Now in order for you to follow this a bit easier, I will gonna use the previous example that we did a while ago, so you can follow along. Now because of the way I designed this thing, 0 is actually the blank symbol, so I have to modify the instruction table a little bit so we can actually program it, like the actual Turing program, into this thing. Alright, now we can actually start doing the programming, which is the fun part. We were gonna start programming from top left all the way down to bottom right. Okay, so starting from the top left cell, we can see that first we need to go to symbol 1 state 0. So here is state 0 row, and then we go to symbol 1. So we type in 1 in binary here, and then we hit this button to confirm, and now we are in cell 1 of state 0. And if we just go here, we should see that all of these lines are on except for this. As you can see, this redstone dust is off, but all of the other redstone dusts are actually on. So we have successfully selected this cell right here. Alright, now let's write in the instruction, or like all the parameters. The first parameter is write a 1. Okay, so we go to the black line, which is a symbol line, and then we write symbol 1. As you can see, it has been confirmed. You can check by seeing the comparator is actually on, and the redstone dust is have a signal strength of 1. You can use a texture pack or press F3 and look at the power, and as you can see, it's power 1. Alright, so we have successfully input 1 into the cell. Now we move on to the state, and the state is state 0. Now state 0 is actually just this, because Lectern actually doesn't have like a 0 condition, so we have to do this, and I basically just cancel this comparator, so now we get a 0 here. Alright, next is the direction. The direction is to the left, so we're gonna move to the left like that, and you also need to check that the signal goes through, and yes, it does. So yeah, that's basically the first cell. Now let's go on to the second cell. Okay, for the second cell we go to S0, so it's still the same row, but now we go to cell number 2. Remember to hit confirm, and now we can start actually like program that cell. So first is the symbol. The symbol needs to be 2, so we write a 2 here, and then S0, so it's still the same thing, and finally direction is left. So yeah, that's basically correct. Okay, now for the blank symbol. Remember, the blank symbol is actually 0, so we input 0 in here, we hit confirm, and now we can do the blank, like the blank instruction. Alright, so first the symbol is blank, and here's how you write blank in my like design. You just click this lever, and now as you can see, we receive 0, which is blank. for the state, we need to move to S1. So we do this and check. As you can see, we have a signal string of 1, so that is S1. Finally, the direction, it is right. So we move to the right just like that, and right, like the signal strength corresponding to right is 15. Okay, and yeah, we have successfully programmed the first row of the instruction table. Now we can move on to the next row, which is S1. Okay, starting from the first square of S1 row, we have 1 S2 plus 1. So we first go to cell number 1. We do this, and now as you can see, we are going to cell number 1 because we have inputted 1 in binary. Now we can write. Okay, we're gonna write 1 here, so symbol 1. We're gonna write S2 here, so S2 is this, and direction is right. Remember to check the signal strength. Alright, and that should be the first cell complete. For the next cell, we are gonna select 2. We hit confirm, and now we can program. It tells us to write a 2 here, so write a 2, go to S3 and move to the right, and that should be done. That's basically S1 complete. Now we can move on to S2. Here's S2. The first cell in S2 tells us to go to cell number 1, so we do that, and now we can type in the instruction. So the instruction tells us to write a 0. Oh wait, not a 0 but write a 1. My apologies. So we write a 1, we go to S2 and we move to the right and check the signal strength. Yep, that's basically correct. Okay, next is 2, so we write 2 here, we press confirm, and now we can write in the instruction. The instruction tells us to write a 2 here, go to S2 and move to the right, and yeah, that should be it. Finally, we have to give instruction to the blank, so we do this, and now we're gonna write in blank. So in blank we need to write a 1 here. We need to go to S4, and we need to go, oh, we don't have to move, so we can just do this, and that will indicate that the table not gonna move anymore. And that is S2 complete. Now we can move on to S3. Okay, now for S3, first we go to the first cell, we press this, and we're gonna write a 1 here. We go to S3 and we move to the right, so we do this, and that should be correct. Next we're gonna go to the second cell in S3. We press this, confirm, and now we're gonna write in symbol 2, S3, and move right, and that should be correct. Finally we go to blank, so it is actually 0. We press this, we write a 2 here, we go to S4 and we don't move, so we just do this, and yeah, that should be correct. Remember to switch that off. Yeah, that should be correct. Finally at S4 we are basically gonna put a halting signal. We need to remember that we need to go to cell number 1 first. We do this, and then we're gonna do this, and then we go to S2 and we do this, and remember to put in the halting signal. So yeah, we put in the halting signal here, and that should be the program complete. We're gonna check a little bit, so like to make sure that everything is correct. Yeah, as you can see, the signal is storing to these 2 cells right here, but not the others. If we go to here, we can see that there are some information in these cells. Yeah, as you can see, we have signals here, signal here, signal here, so all of the cells are working. And now the final step to see the program working is to type in our data string. So the data string is, I have modified the data string a little bit so it works for our Turing machine here. So it is 2, we press load, 1, oh wait, we need to wait a little bit, so 1, wait for this to come back, okay, and then 1, wait a little bit, and you know I'm just gonna tick rate this like 600, yeah, 600, just to make things a bit faster. So then we type a 1, and then we type a 0, or a 1 here, and then a 1, and then a 2, and then a 1, and this is our data string right here. Now in order to see things in action, all we have to do is press this node block right here, and I think I'm gonna tick freeze. Okay, we press the node block, and now we're gonna see the magic unfold. We should see, like in the exercise, we should see that this number right here, which is 2 now, will get copied to this copper bulb. So this copper bulb right here should turns on. Okay, now we gotta take unfreeze, and we were gonna see the program in action. As you can see, it's moving the tape to the left, and now it should move the tape back to the right, and yeah, it just copies the number there. And now we should see that after this one we should see a 2, and any moment now we see a 2, and there we go, the program works. And if we check here, we can see the halting signal is on, and the whole Turing machine just stops. And yeah, as you can see, we can write program here, and we can clear program. This is how you execute the program, and here is how you clear the tape. And if we just look, it's a bit laggy, but if you just look, all of the lamps are, like, of the copper bulbs are getting like cycle through. And if we go to over here, we were gonna see some copper bulb getting turned off, as you can see. And after a bit of time, the tape will gonna stop because of this copper bulb right here. And now you can basically rewrite the program. Oh no, not the program, but the data string. So I'm gonna rewrite it like 2 1 1, and then 2 1 1, and then 2, and this, oh wait, we are missing a 1 here, and this is the data string. And when we hit this button again, we should see the thing working again, because the program is actually storing in here, and the tape just does what the instruction table is telling it to do. And it was gonna move to the right now, and any moment now we should see number 2 appears behind this number 1 right here. And there we go, and the program stopped because the halting signal is here, which basically cuts off everything. And yeah, that's basically everything that you need to know about this thing. Overall, like, it is a very massive project. I had a lot of fun designing this, and I also learned a lot about Turing machines. So I hope that you have enjoyed today's video, and I hope that you have learned something from today's video. It can be Turing machine knowledge that you can brag to your friends. It can be Redstone knowledge, even though I did not go into too much details because I don't want to bore you with all of the Redstone stuff, because, well, that's not the point. That's not the point of the Redstone. The point of the Redstone is to show you how powerful Redstone can be. And yeah, that's the end of today's video. Again, thank you very much for watching. The word download for this is in the description. And also I want to thank the Super 998 again for giving me this idea. So yeah, thank you so much to them for doing that. And yeah, I think this is the most powerful thing that I have ever built so far, since, well, this is essentially a programmable computer, and a Turing machine is basically the most overpowered thing in the universe. Nothing can surpass a Turing machine. So yeah, I don't think I need to build like a redstone computer to compete with this, because I have a computer right now. But don't worry, I will get back to the series. I just have a bit of the work to do, but yeah, I will gonna get back to that. Okay, I will not gonna drag this outro anymore. Subscribe, like, or do all of that stuff, YouTube stuff, to get me to 400 subscribers. I want 400 subscribers, because yes, it's big numbers equals funny. So yeah, okay, all right, bye bye guys, have a nice day, and I will see you all in the next video.